Hey there, everyone. Welcome to my channel. My name is Ryan Schul. I am recording part 4 of 5 for this series related to Bayesian modeling. Okay, so we have 5 in this whole series. This is the first series set of videos I've done. And this is video about 160 or so. I'm trying to do 365 data science / machine learning / deep learning / AI videos in 365 days. Okay, so I started August 8th and the year is 2024. Now it is January 20 and it is 2025. So about 160 days into it. This is video approximately 160, give or take a couple of them, and number 4 or 5 of Bayesian models. So what are Bayesian models? Basically, a Bayesian model is a statistical tool that we can use to make predictions about specific outcomes. We do this all the time in machine learning. This is a little bit different because we look at probabilities and try to understand what the outcome is going to be based on a hypothesis that we create at the beginning of the machine learning process, right? So we make a hypothesis, which is an estimated guess, and we run the algorithm to see how close we are to the actual number that we estimated or that we predicted, right? So if we can prove the hypothesis, we have achieved our mission and proven what we set out to prove. And if we can't, then we can't. Sometimes you can't prove the hypothesis, and that's okay. Okay. Hopefully you can. If we can't, then we have to create a new hypothesis and rerun the analysis. That's all of it. So Bayesian models will help us with this endeavor. So there's a few things that Bayesian models are great for. They're fantastic for incorporating prior knowledge into the model and feeding that knowledge into the model and then producing an updated outcome, right? So the model is constantly receiving new information, it's grabbing and fetching new information and making predictions based on that information. There is uncertainty quantifications, right? So we try to somehow quantify the uncertainty or the probability that is inherent in these models. We have a dynamic updating. Interpretability of the model is pretty straightforward, and these models are very flexible. So what are Bayesian models used for in a nutshell? Basically, you create a hypothesis, and you'll say, I have something, in this case, it's circular, it's also small, it's also fruit, and it's also red. And Bayesian model will say, you know what, this is probably an apple. I'm 50.4% certain that based on the criteria of circular, small, fruit, and red, the object is an apple. Okay, so we take all of these and they're multiplicative. We multiply all of these probabilities times each other and we get 0.504. 0.9 times 0.8 times 1 times 0.7 is 0.504. So 50.4% certain that this is an apple. If we say the object is not an apple, not small, not fruit, and not red, we'll take all these probabilities, 0.4 times 0.6 times 0.3 times 0.2, and multiplying all these terms together, we get 0.0144, 1.44% chance that the object is not an apple. Okay, so this is how we create probabilities, and based on the outcome, we can either, again, we can either prove or disprove our hypothesis. Okay, so I'm going to import some data here. This comes from the classic MT cars data set. I've used it several times in my other videos. So we have a few features here: miles per gallon, cylinders, displacement, so on and so forth, all the way to gear and carburetors. Okay, and I'm going to say all these variables all of these features are independent. Okay, all these are independent, and MPG is dependent on these features. So the miles per gallon that I get for my car is dependent on the cylinder, displacement, so on and so forth, down to carburetor. Okay, so these are the independent variables. This is the one independent variable. Okay, you always have one dependent, and you can have one or multiple independent variables. Okay, we're going to use an ordinary least square fit. We're going to fit the model, and we can use it to make predictions too. I don't think in this scenario we're making predictions, but that's certainly doable. In other videos, I show you exactly how to do that. So we get an R square, which is the goodness of fit of 0.8690. So closer to 1 is better, right? We know a high R square is desirable. 0.9, 0.95, 1.0 is great. That means all of the data points that are laid out on the XY plot will match the goodness of fit line or the regression line pretty closely, right? The higher the R squared, the higher the match, and the better the goodness of fit. Okay, so we just proved the R squared, so it's a pretty decent model, pretty close to an ideal model. Ideal would be 1.0. In reality, like sometimes really you only just get that in an academic setting if the professor sets up everything perfect and you run it and you get an R squared of 1.0. In reality, you almost never see 1.0, but higher is better. 0.86 is definitely fine. We can work with that. Okay, so we have our independent variables dependent right here. And we're going to look at the prior mean and the prior standard deviation. So remember what I said initially with this Bayesian model concept, we look at prior events and then actual current events and then posterior events. So what happens after the model runs? Okay, so here's our prior distribution. We have a mean as standard deviation. You always start with these two, okay? Mean is the average and standard deviation is the dispersion around the mean. It means how far are the data points scattered around the average data point, okay? You'll have an initial random variable, initial random coefficient. This is called likelihood, and again, we're looking at predictions, okay, and residuals. So the prediction is like the mean, or what do we predict, and the residuals are the data points scattered around the mean, right? There's always a distribution. Sometimes it's bell-shaped, which means just normal curve, and sometimes it's skewed one way or the other, and sometimes the distribution is just randomly scattered all over the place, okay? So we have the initial prior distribution, the likelihood of the event happening, and the posterior event. Okay, so we have these three conditions for Bayesian model. We have the likelihood current and likelihood new, okay, based on sigma, standard deviation. The beta is coming from over here, okay, the normal random distribution, okay, with the number of parameters that we have put in there, and parameters is equal to x times one shape. Okay, so I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters. Okay, so we go ahead and run this in the model, Control Enter, and we will wait for the outcome. I am going to cut this. I looked at this scenario before. It's okay. I don't really like it. I'm going to delete that and make this this training session just a little bit more efficient. I was hoping for something a little bit different. I didn't really get that kind of outcome, so let's drop those. So we have the estimated coefficients right here. I believe there's 10 of them, and the R squared is 0.8252. So now it's slightly less. Before we got 0.8690, now we have 8252. Again, this is fine, still statistically significant. And we just saw that when we ran the Bayesian model for random forest regression, there's a few things that shake out here. So we have a real scenario where new data points have become available. Initially, the first set of data points is 8690. We fed in some new data, right? The initial was right here, prior distribution. The random normal distribution was the initial coefficients. We feed that into likelihood, and then we look at the posterior or the subsequent outcome, right? After we change the inputs slightly, and we see the new data points become available, and the posterior distribution would be updated. Okay, so we went from 0.86 to 0.82. So it dropped down a little bit, but that's fine. It's just totally fine. We're just picking up the R squared or the goodness of fit based on the updated data points that we fed into the model. Okay, we're doing sequential updating in real time. As new information becomes available, we feed that into the model. You'll see that in the other videos. This is number 4 of 5. You'll see that in the first 3. We just saw that again, and we'll see that one more time in the next example, number 5 of 5 for the Bayesian model series. And the batch updating was handled over here too. At this point right here, this is the posterior. So we can update one single record at a time, one row of data points, or a batch process, which is lots and lots and lots of rows, are iteratively cycled over. And we're doing these R squared scores over and over and over as new data becomes available. So like I said before, all of these little blue dots over here are where the data points land when we look at observed MPG and predicted MPG. So it's pretty close. It's about 82% goodness of fit. The closer you are to this diagonal red dotted line, the better the fit, right? And the better the model is at making predictions into the future. 82%. 82% is pretty good. It's off a little bit, but I'm not going to lose any sleep over that. It's fine. So what did we learn here? The prior event is the initial event that we fed in with the initial mean and standard deviation. Okay, so the mean here was 0, standard deviation is 10. For the regression coefficients, this is beta, right? And this indicates that initially there is some uncertainty about the values of the coefficients, and that's always the way, right? There's going to be some uncertainty when you do these modeling experiments. The likelihood is the next step. We compute the likelihood of observing data frames given models parameters using the residuals, sum of squares, okay? And the next step is that this is a sample from the posterior distribution. So pre is beginning and post is ending. We propose a new value for regression coefficients and accept it with the probability proportional to the improvement in the likelihood. Sorry, my eyesight is going as I'm getting older and older. Eyesight is getting worse and worse. And then the posterior sample. Okay, so here's the first step. Here's the second. Here's the third step. Posterior sample is after the fact. After running the modeling process, we take an average of all accepted samples and the final regression coefficients, and we can measure R squared. So we did that at the beginning, 0.86, with the updated information, 0.82, and we can do this iteratively over and over and over, and we'll see the R squared probably jump around between 0.86 and 0.82, and it might go a little bit below those or above those, but it probably will remain within that threshold, give or take. So there you go, Bayesian modeling for random forest regression using Python. Hopefully that was useful, insightful, and interesting for you guys. I try to make these videos engaging and meaningful and actually have a purpose when we're trying to solve real problems using real data. Now, obviously, your data might be slightly different than my data here. I'm using the MT CARS data set, but if you understand the concept, hopefully I've explained that well, and you can take that and apply it to your own specific problem and solve your specific problem that you need to solve. Okay, so that's it. I'm going to wrap it up. Thanks for your time today. Enjoy the rest of your afternoon. Goodbye, everybody.